This is a weekly summary of interesting news that is relevant for my lectures at the Eastern Switzerland University of Applied Sciences. My name is Thomas Bocek, and today we discuss 4 topics. The first topic is how URLs can function as state containers in web applications. The author describes discovering that syntax highlighter configuration tool stores the complete application state inside the URL itself. When you select options on the website, every choice gets encoded into the URL parameters, and you can share this URL with someone else and they see your exact configuration without any server-side database or user account. And this demonstrates a form of stateless design where the URL becomes the single source of truth. The server does not need to remember anything about your session. The client holds all the state and each request is self-contained. The article explains that URLs have different parts for storing state. Path segments show hierarchical navigation, that's down here. Query parameters can carry filters, sort options, and configuration settings, and fragment identifiers handle client-side navigation and page positions. And together, these components can represent complex application states without server-side storage. And he also has examples here, for example, GitHub line highlighting, where URL like here github.com, and then you see here the fragment line 108 to line 136. This encodes both the location and which lines to highlight. Google Maps URLs contain coordinates, zoom levels, and map types. E-commerce sites put filters, price ranges, and sort orders in query parameters. All of this state travels with the URL and requires no cookies or local storage. One important detail the article does not mention that HTTP specifications does not define an upper limit for URL length. The original 1999 specification states that servers must handle URIs of any resource they serve and should handle URIs of unbounded length. However, practical limits exist. Browsers impose their own restrictions, ranging from 2,000 characters in the ancient Internet Explorer to much higher limits in Chrome and Firefox. Web servers like Apache or Caddy also have configurable limits. The default for Apache is, for example, 8 kilobytes, and for Caddy it's 1 megabyte. And for practical purpose, to be backwards compatible, keep the URLs under 2,000 characters. This ensures compatibility across almost any browsers and server combinations. And the article warns against common mistakes, single-page applications that store all state in memory and not in URL. They lose everything when the user refreshes the page. And also, on the other hand, putting sensitive data like passwords in URLs exposes them to browser history and server logs. Very long URLs that require base 64 encoding large JSON object signal that state probably belongs someplace else. And the key lesson is that the URLs are not just addresses, but can contain state. They provide shareability, bookmarkability, and browser history integration for free. And when designed well, URLs become contracts that define what state is public, shareable, versus what stays private. The next article, the following here, discusses performance problems with Nextcloud, which is a self-hosted cloud storage and collaboration platform. I also do use Nextcloud. I self-host Nextcloud myself, and the author analyzes why Nextcloud feels slow even on decent hardware and finds that the main problem is the amount of JavaScript code that the browser must download and execute. When loading a clean page, Nextcloud requires downloading between 15 and 20 megabytes of JavaScript. This compresses to around 4 to 5 megabytes during transmission, but the browser still needs to execute all of this code on each visit. For comparison, the author considers 1 megabyte of JavaScript to be heavy for a web application, and I agree here with the author. The Core Commons bundle, for example, from Nextcloud provides shared functionality across different Nextcloud applications with around 4.7 megabytes. Then the notification system adds another 1 megabyte, and individual apps even more. The calendar app requires 5.9 megabytes just to display a basic calendar view, and the files apps include multiple scripts totaling over 18 megabytes, including components the user probably never uses, like almost 1 megabyte of an emoji picker. The Notes app, which is a basic text editor, requires 4.3 megabytes, totaling over 20 megabytes with dependencies. And I also mentioned I also use Nextcloud and verified these numbers. Loading just the files overview requires almost 27 megabytes of JavaScript, which I have down here. So here I have 26.7 megabytes. And I use machines ranging from very weak to very strong, and my weak machines shows noticeable lag when opening Nextcloud in the browser. To be fair, I rarely use Nextcloud through the browser since I mainly use it for file synchronization between machines, and I use Thunderbird as a calendar client, so I rarely use the web interface. And the performance impact also becomes serious on mobile devices, and this makes basic tasks like checking a shopping list at the store via web interface extremely frustrating. And this demonstrates client-side versus server-side processing trade-offs that I talked about last week in the application architecture lecture. Modern web applications often move processing to the client by sending large JavaScript bundles, and this reduces server load in a distributed system but transfers the performance costs to the client device, and weaker devices pay a higher price, creating an accessibility problem. The author started to replace some components with specialized alternatives. Vicuña here replaces the tasks app with only 1.5 megabyte of JavaScript, making it feel much faster. And Image, I'm not sure how to pronounce it, replaces the Photos app. And these specialized services show that focused applications are often lighter than all-in-one platforms. And I personally will take also a look at OpenCloud for syncing files and Stalwart for email and calendar service. The next article, it's the following here, discusses data sovereignty concerns around Microsoft's cloud service in Europe. Microsoft announced new data sovereignty features for European customers in response to growing concerns about US government access to data. And the core issue is the Cloud Act. It's a US law that allows American authorities to access information held by US cloud providers, regardless of where in the world that data is physically stored. Even if Microsoft stores European customer data on servers located in Europe, US law can require Microsoft to hand over that data to American authorities. And this creates a conflict between where the data physically resides and which legal jurisdiction controls access to it. Another relevant law is FISA Section 702, which enables targeted surveillance of non-US persons outside the United States. And Microsoft admitted in a French court that it cannot guarantee data will not be transmitted to US government when legally required. And this admission came despite Microsoft's effort to provide data sovereignty through regional data centers and legal structures. Although Microsoft publishes transparency reports showing no European customers have been subject to such requests yet, the legal possibility remains and makes customers nervous. And since President Trump returned to power in 2025, Microsoft acknowledged that geopolitical relations between the US and Europe have become volatile. And in response, Microsoft announced several measures. Microsoft also increased the scale of Azure Local from 16 physical servers to hundreds and added storage area network support so organizations can use existing on-premise storage. And Microsoft 365 Local reached general availability, bringing Exchange servers, SharePoint servers, and Skype for Business servers to Azure Local. However, European cloud providers criticized Microsoft's approach. The CEO of Nextcloud called it sovereignty washing, arguing that in Europe, sovereignty means the absence of strong dependencies on overseas third parties. And he claimed only open source software prevents dependencies on individual providers and allows independent security audits. And the article, that one here, mentions that European tech firms have clear financial motivation in promoting data sovereignty concerns as they want to reduce Microsoft's and AWS dominance in the European cloud market. And with Trump's presidency extending for several more years, these companies have now a window of opportunity to persuade customers to choose local European providers instead of American cloud services. And this debate will likely continue growing as government use digital tools more extensively and store more sensitive data in the cloud. Questions about who can access the data and under what condition becomes increasingly important. The technical ability to store data anywhere conflicts with legal requirements that follow the company providing the service rather than the physical location of the servers. And here at OST, we also use Microsoft 365. This means US authorities can potentially access stored data, including student grades and internal documents, through legal mechanisms like visa orders and the Cloud Act. And even though OST's data may be stored in European data centers, Microsoft as a US company must comply with US law enforcement requests. The last article, it's about blockchain, and it's the following here. This article is from Rect News and describes the cryptocurrency stablecoin scheme involving Stream Finance and Elixir network that created tokens through recursive minting loops. And the story shows how blockchain systems can be exploited through circular dependencies between protocols. Stream Finance created XUSD and Elixir Network created the DUSD, both marketed as stablecoins backed by professional partnerships, including BlackRock's Build Fund or BUIDL, I'm not sure how to pronounce this. The problem was the recursive loop. Users deposited USDC into Stream's vault. Stream converted it to USDT, minted DUSD from Elixir, bridged DUSD to other chains, borrowed stablecoins against it, minted XUSD with those borrowed funds, then used Elixir's lending market to borrow more USDCs against XUSD, and the borrowed USDC minted more DUSD, closing the circle. And the same $1.9 million in initial capital generated $14.5 million in XUSD through 3 rounds in a single day. And each token was backed by the other, but both were backed by the same USDC, counted multiple times. Analysis suggested each XUSD token had only 40 cents of actual collateral, possibly even below 10 cents. And this created circular dependencies across multiple protocols. Yield files YUSD borrowed from markets accepting XUSD and DUSD as collateral. Another wallet lent against YUSD while also lending to XUSD markets, and each protocol's solvency dependent on all other remaining solvent. And warning signs appeared throughout 2025. In May, an Oracle malfunction caused over $500,000 in liquidations. In August, DUSD depegged to 89 cents, and the XUSD token traded between $120 and $129, despite supposedly being pegged to $1. And here we see that it's traded at 126 here, and this should be 1. And what we also can observe here is on this date here, 3rd of November, the big crash. And now everyone who is holding these stable coins, the staked stream USD, lost a lot of money. It's now worth 8 cents. On October 28th, researchers posted transaction hashes exposing the process. And on November the 4th, 2025, Stream Finance announced that an external fund manager lost approximately $93 million in user assets, triggering immediate suspension of all withdrawals and deposit. The XUSD stablecoin crashed from its dollar peg to now around 8 cents. And DeFi researcher identified nearly $285 million in direct debt exposure across multiple lending protocols, where the same collateral was used multiple times across multiple platforms. And it's unclear due to the circular dependencies how much dollars were lost, but I guess it's more than a couple of $100. And this shows that blockchain transparency does not equal safety. All transactions were on-chain, but most users didn't understand them. Then code correctness differs also from system correctness. The smart contracts work perfectly, but the economic design was unsustainable. And lastly, information asymmetry exists in decentralized systems. Expert analyzed data and they exited while retail depositors remained unaware. And this parallels Terra Luna, which used algorithmic mechanisms to maintain its peg, but collapsed when redemption pressure exceeded backing. Stream and Elixir used cross-protocol leverage loops instead, but the fundamental problem was the same, creating value through circular dependencies rather than real backing. And both systems worked until too many people tried to exit at once. That's it for this week. Stay safe and see you next week.